listening to Data Skeptic, Graphs and Networks, the podcast exploring how the graph data structure has an impact in science, industry, and elsewhere.
So he's doing, let's introduce it. He's doing graph rewriting and also some graph neural networks, or would you describe it differently?
He's applying rules by using some rules in advance to change the topology of the graphs he's working on.
So Adam mentions a few times he works on typed graphs, where each, I guess my interpretation is that each graph has sort of, if you take an object-oriented perspective, it's like class, like it's a person or it's a post, and has sort of more rigid quality. Was that your interpretation? And do you find that the idea of a typed graph to be common?
When you say type graph, usually like a type graph DB, it's like a graph DB. Although I guess the type graph community will kill me for saying it, but it originated from GraphDB. But I think there are more. They allow a more flexible topology. I'm not an expert about type DB graphs, but I think it's more. I would sum it up as a more flexible way of saving your data.
Well, let's jump right into the interview then.
My name's Adam Machowczyk. Difficult sounding last name because I'm Polish. And my affiliation is University of Leicester. Currently a graduate teaching assistant and a third year PhD student. I'm studying graph rewriting and machine learning, particularly graph neural networks. So it's quite a narrow study of two very hot areas, trying to bridge the two together.
And we're going to get into graph rewriting primarily, but maybe we should start a little more fundamental. Could you give a rough definition of a graph?
The way I like to explain graphs is by saying they're circles and arrows. Circle can be anything, and then an arrow just points between two or multiple circles. A circle can be me. I can put myself inside of the circle, and then I can put an arrow to another circle, say you, and label the arrow, so basically name the arrow saying nose. So then the result is Adam knows someone else, and that's already a valid graph. The largest graphs on the planet are trillions of nodes and edges large. That's such a huge number, it's impossible to imagine. But yet, here we are.
And of course, graphs apply in so many different places in different ways. Do you have a general interest, or are there specific, industries or data sets or something like that you're most focused on?
I'm focused specifically on machine learning with graphs. Not exactly a huge fan of algorithms per se, so not really graph theory, though that is also relevant at times. The data set we use, we like to have social network data sets, such as Twitter, the voting problem data set, or the famous Karate Club data set.
Well, we're going to break in here. Asaf, it's time to do something official, yeah?
Yeah, I think it's the first time that the dataset of Zachary's Karate Club was mentioned, right?
Yeah, this is a thing you put me onto. What's the deal with the Karate Club award?
Okay, so the Karate Club dataset is a famous dataset in network science. What's interesting in the dataset is that while Zachary looked at the Karate Club network he made from the connections between people in this Karate Club, many researchers use this dataset to try all kinds of algorithms. Because it's such a famous dataset, there's a competition in network science conferences where the first person to mention this dataset, the Karate Club dataset, gets the Karate Club trophy. And the trophy goes to, as I said, the first person who mentions it in the conference.
So we are not officially affiliated with the actual award. We're doing a very unofficial version. Our own award here goes to Adam as the first guest to make it on this season and mention the Karate Club dataset.
But realistically, we can work on any, and that's part of my research to make it work as such.
So graphs, I think we get the idea of graphs, the nodes and edges, and machine learning, to some sense, I'm sure our listeners are familiar with, but it's not clear what we're doing with machine learning. What are some of the common tasks where graphs get involved?
So whenever we need to figure out a pattern, that's where machine learning is good for. As humans, we also tend to look for patterns in things that we do or look at, but there's not always a pattern, or it may be so well concealed, it will not be possible to figure it out without spending years on it, and even then it could be tricky. So machine learning is particularly useful when the size, the amount of data we have, exceeds human capabilities. So a typical dataset may have 1 million of records, or it goes into 10 and hundreds of millions as well. That's unimaginable size. So that's when machine learning is awesome, because we can put these 100,000 of rows where each of them corresponds to 100 million records of data and let the computer figure the patterns out.
Well, computers are getting cheaper and cheaper, and we can work on bigger data sets. And there's a pretty common path of what I call tabular data science, where I get my data into like roughly an Excel format, and I want to have columns A through Y predict column Z. Why can't I just cram the notion of a graph into that format?
To an extent you can, because there are algorithms that allow us to translate a graph into tabular format or the other way around. However, doing that, we are losing something. Graphs are awesome because they let us show these relationships, which are the arrows. So me knowing somebody else, or me going somewhere, or me being somebody, those are all vital relationships between pieces of data. And in a tabular format, it may not be possible to present them as such, and they may be fluid, as in social networks, dynamics, they may change, or they may also have different sub-components of their own. I can be born somewhere in a town, but maybe I have multiple cars, or maybe the date of an event can be shown as multiple time formats in different countries. And with graphs, all of these are just natural arrows which can have multiple attributes to them.
Well, in the tabular data science, there's usually a process of feature engineering. I've got my raw data and I do a few transformations or calculations to prepare it for ML. Is there a similar process doing graph machine learning?
Yes, absolutely. And most of it depends on the objective, on the task. So to give an example, I've seen people who will first transfer their graph into something called an ego graph. The reason is an ego graph will show you the most relevant connections from one particular node, a circle's perspective. That will be the center of the ego. That will be the ego. And it will show you the connections to other nodes through the edges. You can also limit them. So let's say we only want to show connections up to 500 meters long. Say we're doing urban exploration in a town, and we are only interested in, say, streets that connect me to a set of streets, but no longer than 500 meters, which may be a valid task on its own. We do that as well, depending on the task.
When do graph neural networks come on the scene? Is this a relatively new idea, or is there some history to it?
So the history begins in late 90s, where a pair of researchers wanted to do something similar to learning on graphs. They became hot when the first adaptations of the convolutional neural network came in, which was generalized into the graph convolution network, which really revolutionized the field as we know it now. And these attempts were made by a group of researchers who basically established the field in the early 2000s, 2006, 2008.
And then in a CNN, I'm familiar with the idea of like a sliding window. Maybe it's a 3x3 pixel grid, and I kind of move it across my entire image, row by row, column by column, and I'm doing some computation in each position. But a graph isn't as rigidly in a grid like that. How does the process work for graphs?
Well, a graph can be a grid. And in fact, we very often like to represent images as graphs, because each pixel of an image will be one node of the graph, and each adjoining pixels will be connected through edges. So we can do a direct sort of intuitive view of that model into graphs, but there will typically be something more to it. The algorithms are very similar, just a bit more tuning to work on that graph structure, the adjacency matrix and the graph Laplacian.
A lot of machine learning, I know you at some point have to get fixed length data to work with. Like even in natural language processing, you can have a variable paragraph, but an embedding will give you a fixed width vector. In graphs, I have, maybe one or two friends. Maybe I'm very popular and I have hundreds. How do we reconcile this sort of dynamic nature of the graph?
That depends on how we want to interpret a dynamic graph, because we can either treat it as a graph that possibly changes over time, or we can directly treat it as a graph that does right now change over time as we learn from it. And depending on which way we want to go, we may want a different approach. But typically, the graph, when it's analyzed by the graph neural network, is also fixed as an adjacency matrix, which is then processed through the network. And with additional techniques such as reinforcement learning or just blatantly retraining the graph, we can then get it ready for new things. And there's a lot of optimization techniques around that.
So I've got, let's say, my sample graph data, and each node has a few properties. Maybe even some of the edges have properties. Do I use all that raw data, or is there some transformation done to it initially?
So you can transform it initially, and it may be sometimes valuable to do so. Let's say one of my features, one of my properties, is the one I actually want to predict later on. So I will not give that to the model to learn. Instead, I want the model to figure it out. So I can hide that, or I can add something new, which is commonly done by graph neural networks, such as the degree of the node, of each node, which means to the number of how many other nodes is that one node connected to. And this is all usually, not always, can be disabled, a thing that the model adds itself to learn from without you having to specify it.
So in your example, maybe there's a property you hold back. For example, like I'm thinking of a social network where there are spam users that the customer service team has identified. So we've got this property spam and not spam. Wouldn't it be great to infer that? Is that a good example of node prediction, or how do you classify that style of prediction?
So typical graph tasks that we have will usually either be node prediction or edge prediction, sometimes graph completion, but the one you would be referring to would be attribute prediction, or sometimes called node level attribute prediction, where I want to specifically infer one of many attributes of a node. But realistically, there can be as many tasks and ideas as there are researchers. There can always be something new showing up.
And across all those tasks, for the various different types of things like link prediction and node classification, is it all the same methodology?
The methodology will depend heavily on the data we have available and possibly the who we're working with, because a lot of problems are usually addressed to work for, say, a particular company or a hospital or a person who issues a grant. Depending on who we work with and how large our team is, how many resources we've got, we may want to be a little bit more or a little bit less ambitious. Some models are trained for literal months, whereas some other models will get great results after just one day of training. So those are related to something called hyperparameter tuning, which is slowly becoming a field of its own, which can also extend how long it takes us to finish by very long. So all that depends on our time and resources and deadlines.
Well, one topic that I see coming up in graph machine learning that's probably new to a lot of machine learning people is the idea of message passing. Could you give a rough definition of what message passing is? Thanks to our newest sponsor, math.fashion. Yes, that is a real URL. Visit math.fashion and check out their line of mathematics-themed t-shirts. They sent me the Klein Bottle shirt, which is pretty stylish. I've gotten a few compliments about it, and each one is the opportunity to start a long conversation about two-dimensional manifolds. Get more math in your life, specifically on your body. Visit math.fashion. Could you give a rough definition of what message passing is?
Message passing is an aggregation technique, an aggregation algorithm, which is the foundation of what we know today as graph neural networks. Most, if not all, the vast majority of models use message passing in order to, as the name implies, pass messages between the nodes. So by messages, we mean aggregated attributes. So the information that the node has will be composed into messages, and these messages will be delivered to all the neighbors of the node. At the end of the message passing step, the node aggregates all the messages it's received to kind of change its worldview. It will update its attributes based on the attributes of its neighbors.
So I guess I can get a message from each of my neighbors. Do I also get messages from my neighbors' neighbors?
Not directly. However, you do indirectly, as message passing is usually referred to as K-hop message passing, where I will want to get that information, and maybe even it is necessary for my model to function properly. So in the first usual wave of message passing, I will only get information from my direct neighbors, but at the same time, they get information from their direct neighbors. So once I do 2 hops, I will also have that information from them, and it can go on forever, as long as we have enough resources and memory to process it.
Well, I'm wondering if we can now take the example of using a graph recommender system on a social network. So I'm picturing a social network. It's people are nodes and the edges are undirected links saying I'm friends with this person. How do we get from that representation to something more useful for recommenders?
To do that, we may need to have a bit more data. We may need to upgrade our graph to no longer be a homogeneous graph, which only supports one type of nodes, such as people, but we want to go to heterogeneous graphs, which consider multiple types. So my nodes, my circles, can now represent people, maybe posts in a social network, or maybe even activities if we want to. Maybe they can represent retweets if we wanted to, or something else, like the number of likes on a video. So each one of these is a different thing. It needs to be its own type. So we go to a typed graph that's also heterogeneous, because in tabular machine learning, it's mostly homogeneous.
So I can picture that. So I've got maybe a post that I've put up. I'm the creator, so there's a link there. Hopefully you like it. So there's a link there, a different flavor of link, I guess, maybe. And then what sort of tasks now can we take on? What's actually being recommended?
The most common use case for this would probably that somebody wants to recommend you better advertising to get more money. But let's say we want it to be useful to our users. So maybe we will recommend a post of our friend. So maybe they've typed something very interesting, or someone we follow on, maybe a celebrity or an authority in our field, and we want to see their messages. But obviously there's only so much we can see in a social network. So the recommender system will take a probability to show us that thing for everything it considers valuable to us. It will take possibly 10 posts made by 10 of our different friends. It will assign them a probability or an attention score, and the one that it considers to have the best score is the one that shows up on our recommender list.
So I can envision through a lot of the techniques we've discussed so far that then maybe there's a post and the question is, would Kyle like this post or would he read it? And it's like a link prediction. So the most likely links could be good predictions. And we could kind of do that with a lot of the existing techniques. Talk a little bit about the motivation that got into your work and going beyond that into the graph rewriting. What was the limiting factor that caused you to explore something more interesting?
So let's first explain what graph rewriting is, because that's not so obvious. So any action of changing a graph, whether be it adding new nodes, new people, new arrows, new relationships, or even changing the attributes of the existing ones, we call that graph transformation. So how do we actually change the graph is through graph rewriting. If you've done any programming, you'll know what a function in a program is. It's basically a way to do something with the data. So to graph rewriting, a rule is what the function in a programming language is to that data. We'll define specifically what data goes in, how it gets transformed, and what goes out. And I like to use examples of KFC to show how it works, because it's easy to just show that somebody goes to KFC, they're hungry, and you rewrite the graph with a simple rule that will tell them, I'm no longer hungry because I went to KFC. We use intuitive colors like green and red to show that something's been created or deleted in that graph. So it's all very intuitive and quite easy to understand. And we want to take that and apply all these friendly and easy and powerful techniques, because we can do this to any graph, no matter the size or attributes. We can write a function, a rule for any graph. So if we could do all of that with neural networks working on graphs, our possibilities are essentially limitless.
When it comes to something like an embedding, even though I know how it works and I trust that it's true, the actual embedded values are like random numbers to me. I can't make heads or tails of the first and second value in the vector, except for I know they're good features and they're useful. When it comes to the rewritten graph, is it of a similar form, that it's useful but complicated, or is it something intuitive I can understand?
So a graph that's rewritten is basically exactly the same specification as your original graph. So maybe the number is different. So if we assume somebody just had their birthday, a graph rewriting rule would change the number from 23 to 24. So that's quite intuitive. That's easy. But if you were suddenly to be in a town and you want to build an entirely new street, so that your rule will build a new street and will build, say, 5 blocks of houses on there, that may be a big change, a bit more difficult to imagine, but it should still be intuitive through the rule.
And how do you come up with the rules?
So I write them myself. I personally love to use pen and paper, but obviously to work on the computer we need a bit more. So we use software that lets us specify what to target in the graph, what will happen to it, how many times. A rule can be applied more than once. That same rule can work indefinitely, theoretically. The tool I use is called Groove, but there's many others, such as Grapevine. You could probably even do that with a graph database, just launching a query that will modify the graph. The formalism here, that springs from mathematics, so maybe let's not go into that, is of single push-out and double push-out approaches in category theory, but let's not go into that, that's a mess. So we want this formalized way, called SPO or DPO, to change our graph. So not just running a query on the database, that's not formalized. We want to be fully formalized. And tools such as Groove work on that formalism to rewrite the graph.
And so you're writing the rules by hand. Do you also by hand decide when and where to apply?
Yes, you should know at which context, at which situation to apply the rule for. But if you get it wrong, nothing happens, because usually we run something called a labeled transition system, where it will show you every possibility of the rule applying. So obviously sometimes a rule can be applied to more than one thing. If I have 10 people in my graph, and I want to give each one a birthday, then obviously I can apply that one rule to 10 different objects. So a labeled transition system will do exactly that. It will consider 10 different realities and apply it to each one of them, and possibly so on. If you want to run the rule twice, it will then take each of that new reality and apply it again and again and again until it runs out of possibilities.
So starting from my native graph, maybe it's, I don't know if it's my adjacency matrix or whatever representation I have, what does the rewritten graph look like? Obviously, it's the consequence of the rules, but what is intrinsically, how is it different from the original?
For machine learning, we typically want these matrices. We want to split the graph into the adjacency matrix, the degree matrix, the Laplacians. But for graph rewriting, none of it really matters, because for the graph rewriting, from the graph rewriting's perspective, we work on graph as a graph structure and not on the matrix that has been extracted on the basis of the graph. So when considering graph rewriting, we want to think of the graph, its structure, its edges, as a whole, as a useful thing. So it will have more nodes or more edges, maybe have less nodes, less edges. Maybe we will introduce a new property, but it still mostly remains as it adheres to the type we've decided on. So the type graph is kind of a border, at the same time an instruction to what the graph needs to look like. And as long as your rewrite rule adheres to the type graph, otherwise you won't be able to apply it, it will crash. So as long as that's true, you will get a new graph that adheres exactly to your model, to your specification.
Do you face any, scalability or computational challenges applying this method?
As for graph rewriting, not really. There is the question of termination in graph rewriting, which may be that our graph rewriting system will never terminate. It can go on indefinitely because we keep adding things and deleting them. It could go on forever. So it's up to us to decide when to stop, but we were not really concerned about that.
Wouldn't like a max iterations kind of give you a solution immediately?
You can do that if you like, yes. It will ask you at first how many iterations to run, and at the end, if you want to do more, you just click on continue, and it will do more.
So how does one decide when it's converged to its fully baked state?
You can click on the recent simulations and see if they changed enough for you to consider it done. In our paper, we've decided to use a matching rule. So matching means that our graph will try to see if we can match to the graph. Say, let's give an example. We have 10 nodes, and we want to select a node which has the name of Adam. Let's see, it's my node. We want to match that node to me. So the matching algorithm will do this SPO, the DPO to do that, and it will show that on the screen. But it's not always possible. Let's say I want to find me. However, there needs to be some other requirement met. So let's say it wants to find me when I was 23 years old. So I'll specify that as the name and the age. And if those two requirements are not both met together in the matching stage, it comes up with nothing. So we can put such a condition on the rule to only match if a certain condition was met, which we've done in the paper with the delta. If it's not substantial enough, we can stop, because we'll not really learn anything useful anymore.
A few episodes ago, I interviewed a researcher who was doing some community detection work, naturally with the famous Louvain algorithm. Her primary contribution was this random walk process that was like a pre-processing step to give different weights. And after these weights were achieved, it was plain old vanilla Louvain from there on out. Is there an analogy here? Is the rewriting a pre-processing step and then it's GNNs to finish, or is it more involved or embedded in some way?
So that will depend on the objective. However, GNN is rewriting. Actually, depending on the sort of depth we want to go, a deep graph transformation machine learning model is exactly rewriting. And that's what we wanted to get across in the paper, that as long as you can do a machine learning operation on a graph, you're in fact rewriting. And random walks and other probabilistic ideas are an excellent look into how we can flip a coin, get a perfectly valid yet different result every time, being very efficient, which is, when I first read about this, I was very surprised that the algorithm really just flips a coin to see what comes up the highest probability and do exactly that. But it could also flip a coin and land on the last narrow element with 1% to be selected. And it goes on from there, which is fascinating.
And then the technique, is there any, high-level observation you have where the resulting model would be significantly better? Like graph neural networks fail in a certain area, but the rewrites make it work? Or what's the best selling point, for the technique?
Usually, the issue with neural networks will be that we cannot do a lot of processing because it's exponential, or it stacks up so many layers and so many operations that it's no longer feasible. So even with a graph convolution network or the more basic ones, we can only apply 2 or 3 layers of the operation, because otherwise it just takes too much memory and it's no longer feasible. With graph rewriting, we don't exactly have that problem, but size of the graph, the scalability of the graph remains a big, big problem in the community in general.
We talked about social networks as one application. Are there any other areas where you think the potential is there and maybe untapped, or areas you'd be excited to see techniques like yours applied?
Realistically, any area that uses graphs can benefit from this. The most common ones I see when I read papers are chemistry, sometimes physics, but usually it's chemistry and molecule research, social networks. But really, there's papers on any domain. As long as somebody needs the model, as long as somebody has a task, it can be done on that task. Recently, we've had a discussion with my supervisor. We even considered using it on Internet of Things specific networking backbones, if I remember correctly, where it's just a specific type of a computer network that just has this particular structure. So that's a very specific problem. And as long as you have a problem with graphs, you could use that technique. Creativity is the limit.
Well, Adam, what's next for you?
I've just done an experiment in the last 2 days where we tried to make a graph into another graph, and somehow I've achieved 100% accuracy on all 3 experiments, which probably means I've done something wrong with the code. But for verification, obviously my supervisor is looking into it. And if that goes well, we'll take the problem from symmetric closures, so just trying to figure out if 2 nodes are symmetrically connected, to something more difficult, such as transitive closures. This way we can show that we can actually make a graph neural network deal with problems that they were never able to deal with before. These are new discoveries and new findings. The more problems we solve like this, the better the algorithm becomes, and the more problems it can solve, the more general it becomes. And then hopefully I'll finish my PhD in less than 2 years now, and hopefully get a more research position to continue doing this. And I love teaching as well, so hopefully academic career, but we'll see.
Is there anywhere listeners can follow you online?
I'm cybersecurity and privacy aware, so I don't have any social media. But if anybody's interested in that research, please email me or my supervisor, Professor Reiko Heckel. Our email is publicly available on the University of Leicester page, and you can probably type my name into Google and find that as one of the first results. And yeah, I'll say, please start trying graphs and graph rewriting. It's very fun and intuitive, easy to get into, and doesn't really require much. So if you enjoy that sort of thing, if you enjoy graphs, get in touch with us. We want you.
Adam, thank you so much for taking the time to come on and share your work.
Thank you for the invitation. That was great.